Now we're going to look at KD trees, which is an extension of BSTs that allow us to do efficient processing of sets of points in space. And it's very flexible and very useful in lots of applications. So now we're going to extend the API to talk about two-dimensional keys. So that's just, you can think of two-dimensional keys as points in a two-dimensional geometric space. So we're going to talk about insertion and search. We want to talk about deletion, and then range search and range count. So we want to be able to insert and delete points. You can think of a two-dimensional key as a point in a two-dimensional space. And we want to be able to find all keys that lie within a two-dimensional range. That's a rectangle, as I mentioned at the beginning, or count the number of keys that lie in a two-dimensional range. So again, the geometric interpretation is the keys are points in the plane, and we have a range, 2D range is a rectangle or is oriented to align with the horizontal vertical axes. And we want to be able to find or count the points in a given rectangle. And this one has many, many applications, and we'll talk about some of them later on. And even if it's not points in the plane, just databases, you might ask for all the people with incomes between 1 million and 10 million who are between 40 and 50 years of age. And this kind of algorithm and data structure would be useful for that kind of situation too. So how are we going to solve this problem, implement this API? We build a data structure containing points that can efficiently support range searching and range counting. Well, one easy way to do it is to just think about dividing space into a grid of squares. So we'll pick a parameter m and divide space into an m by m grid of squares, and then process all the points and make a list of points that are contained in each square. We can use a two-dimensional array to directly index relevant squares. And for insert, you just take x, y, figure out which square it belongs to, simply divide by both coordinates by m, and look in the two-dimensional array, and just add the point to the list for the corresponding square. Then range search is only find the squares that intersect the query and process the points in that square. And depending on the value of the parameter m, you have a space-time trade-off. The amount of space required is m squared for the grid, plus n. You have to have a linked list element or whatever for each point. And then the time, though, gets divided by m squared. Your number of points m are spread out over the m squared different squares. And so on average, you examine n over m squared points per square. So you don't want to make m too big, be too much space. You don't want to make m too small, be too much time. So what we want to choose is the square size that would best balance these two needs, and then it's easy to see that what you should choose is m to be about square root of n, so then your space is within a constant factor of n, and your time is constant. So if the points are randomly distributed, then this is ideal. It takes this linear time to initialize the data structure, and to insert and search, it takes constant time per point in the range. And this is absolutely a fine method that is not that difficult to implement in the case that the points are evenly distributed. Unfortunately, it's usually the case that in geometric data that the points are not evenly distributed. And so a well-known phenomenon known as clustering that says that the points aren't going to be evenly distributed all over the whole thing. In the case of the grid implementation, they might all fall in the same square. And so the average list length is short. This is like what we encountered with hashing. If you take all the points in one square and 0 in all the rest of them, your average is still n over m squared, but they're all in that long list, and you're going to have a slow algorithm if it's based on this. So we need a data structure that more gracefully adapts to the distribution of the data. And again, it's well known that most geometric data has this kind of problem. So for example, here's some data which is cities in the US. It's got 13,000 points, but if you tried to use the grid implementation for this, you find that half the squares would be empty, and half the points are in just 10% of the squares. So the clustering in the data is going to make the implementation inefficient. We need to adapt to the data, and this is very, very typical in geometric data, particularly in higher dimensional data, as we'll see in a minute. So people have developed all different kinds of methods for adapting in this way, and what we're going to look at is one of the most widely used, which is basically to use a tree to represent a recursive subdivision of the plane of two-dimensional space. It's going to be recursive, it's going to be based on the points, the way in which we divide into half planes. And it's one of many different algorithms that have been studied for this, but again, it's a simple one and widely used. So for example, if you've played the game Doom or used a flight simulator, these types of graphical simulations and animations are made possible only through the use of space partitioning trees like 2D trees and quad trees, and also in all different types of scientific data processing. These things are extremely important. Whenever you're processing geometric data, you're doing some kind of geometric search. Where's the closest thing? How am I going to find the closest thing efficiently? What things are nearby? And so forth. So rest assured, these types of algorithms lie at the heart of any program that you use that is involving a lot of geometric data. So those are just two examples. So let's look at how it looks now. So a 2D tree is, again, it's going to be a data structure based on a bunch of points that's going to facilitate efficient data processing of these points. So just as we do for symbol tables where we take keys, now we're going to take points. And we're going to build a data structure based on these points. And the idea is to build a tree that corresponds to recursively partitioning the plane. So arbitrarily, our first point, we're going to divide the plane into two parts based on a vertical line through that point. So now in the tree on the right there, all the points that fall to the left of the first point are going to be on the left, and all the points that fall to the right of that first point are going to be on the right. But then when we get to the next point, we'll switch and we'll partition on a horizontal line. So now our second point in the tree, the left subtree corresponds to everybody below that horizontal line, and the right subtree corresponds to everybody above it. Similar, if our third point comes on the left, again we'll partition according to the horizontal line through that point on the left. So if we go left and then left, that means all the points to the left of 1 and above 3, so the square in the upper left is represented by that node in the tree. Again, now when we go to one level below, we switch again to vertical, alternate between horizontal and vertical partitioning of the plane. So it's a regular binary search tree, but it's got this interpretation based on the geometric data where we switch which key we use for the comparison, the x-coordinate or the y-coordinate at each level, and that corresponds to this partitioning of the plane. So now 5 comes in, that's to the left of 4 because it was partitioned on a vertical, and 5 is going to partition on a horizontal. And this is a simple and completely well-defined partitioning of the plane corresponding to a binary tree. Now the 9th point, well, it's to the left of 8, above 2 to the left of 8, and then corresponds to horizontal partitioning. 10th point is to the right of 1, it's below 2, so we go to the left, and it's to the right of 7, so we go to the right. So that's a way to build a binary tree corresponding to a partitioning of the plane. And it's really the same as a binary search tree, it's just that we alternate which coordinate we use as the key. At the even levels, we think of a vertical line, and the left subtree is all the points to the left, and the right subtree is all the points to the right. On odd levels, we use a horizontal line, and the left subtree is all points below, and the right subtree is all points above. And the code for this is the same as for binary search trees. It's simply which coordinate we use for the comparison. That's the only difference. So that's 2D tree implementation. So now what about solving a problem like this range search problem for a 2D tree? So now we have a query like this green rectangle, and what we want to find is all the points in the data structure that fall within that rectangle. Well, we're going to use the 2D tree represents our points, and we're going to use the structure and definition of that tree to go ahead and help us find the points that are in the rectangle. If the root node lies in the rectangle, then we're done. We can return that point, but we have to look on both sides to look for more. But if the rectangle lies to the left of the root node, then we only have to look in the left and so forth. So let's look at how this works in a demo. All right, so we're going to try to find all the points that are contained in that green query rectangle. So first thing is to check if our rectangle contains the node at the root. In this case, it doesn't. So since it's to the left of the splitting line at the root, we only have to search in the left subtree. Now we search the left subtree. We're going to check if it contains 0.3. It does not contain 0.3, but now which subtrees do we search? In this case, the rectangle intersects our splitting line, so we have to search both subtrees, both above and below. So first we search the left subtree, that's the one below. Does it contain 0.4? No. It's to the left, so we only have to search the left subtree of 0.4. And so we search the left subtree and we check if it contains 0.5, and it does. That's the one that we return. It also intersects the splitting line, so we have to search both the subtrees. In this case, they're both empty. So we're done with that, but now we have to go back and we have to search the other subtree of 0.3. That's the above, so now we check is 0.6 in the rectangle. In this case, it's not. And it's to the left, so we have to search the left subtree of 0.6, and that one's empty, and now we return, and we're done. So we don't always go down just one branch. If our splitting line hits our rectangle, we have to go down both branches. But still, this is a very efficient algorithm. Particularly think about the rectangle being small. It's going to be not that different than a regular search in a binary search tree. All right, so what about the analysis of how long is this going to take? Well, again, a typical case, a rectangle's small, that we're only going to examine really a path of the tree, maybe a couple of other nodes along the path, and the running time will be proportional to the number of points returned plus log n. With geometric data, the worst case can be bad. So like all the points could be arranged in a circle, all different types of problems might occur. And with some difficulty, it's possible to prove that even if the tree's balanced, you can get a worst case proportional to square root of n. So analysis of 2D trees is a bit beyond our scope, but for many practical applications, they're easy to implement and worth using. Let's look at another, using 2D trees to solve another problem, the so-called nearest neighbor search. So now, instead of a rectangle, we have a query point, and our goal is to find the closest point to that point. So in this case, our query point is over here in green, and our algorithm's going to want to return 0.5. That's the closest one to the query point. So let's see how that looks in a demo. So again, we start at the root, and what do we want to do? Well, we're going to check, whenever we're at a node, it represents a point, so we're going to check that point, and we'll compute the distance from that point to our query point. And if that distance is less than the best found so far, then we'll keep that as the champion. So the first point, that's the closest we found so far to the query point, so we'll save number 1 as the distance. And we'll only worry about the possibility of finding something closer than that. And so just using that distance, we recursively search any part of the tree that could contain a closer point. And so that's what we'll continue to do. So in this case, the query point is to the left of the splitting line, and we'll always go towards the query point first. So in this case, we have to search both. There might possibly be a closer point than one over in the right. If you come like straight across, there might be a closer point. We're going to have to look at both as far as we know now, but we'll go towards the query point and see if we can find something closer. So in that case, now we go to root node, point 3, compute the distance of that point to the query point. It's closer, so we update 3 to be our new champion. And so now we're only going to look in parts of the tree that could give us a point that's closer to our query point than 3. Notice already that'll mean when we get back to point 1, we won't search the right subtree because there could be no point on the right subtree, the right of this splitting line that's closer to the query point than 3. And so that idea of getting closer and closer to the query point is going to cut out different parts of the tree as we process. But anyway, starting at point 3, as far as we know, we're going to have to look at both subtrees. So sometimes we look at both subtrees, but as we get closer and closer, we only look at one. So let's look at point 3 now. Again, go towards the query point, so we'll go to the top first, and that takes us to 6. 6 is not any closer than 3 was, so that's not going to update our champion. And so we'll search 6's left subtree, which is empty, and then its right subtree. Well, the nearest neighbor can't, we don't have to go down the right subtree of 6 because you can't have a point in that rectangle that's closer to the query point than 3. So now we can return from that, and now we have to look at the bottom subtree associated with 3. And so that takes us to 4, and that one is not closer, so we still have 3 as our current champion. So now we'll search the left subtree of 4 first, because the query point is to the left of that splitting line, and that takes us to 5. And 5 is our new champion, so that's the closest point that we know about. Could there be a node that's closer to 5, to our query point than 5 in the right subtree of 4? We have to go above, sorry, to look at the top subtree associated with 5 and find that it's empty. And now we're back at 4. Do we have to search the right subtree of 4? No, because there can't be a closer point than 5 in the right subtree of 4. So we're done with 4, and we return to come to 3. And now we search the supposed to search and return from there. We now are at 1, supposed to search the right subtree of 1 next, but we can prune that. Nearest neighbor couldn't be in there. So then we're done, and we found that the nearest neighbor is 5. And this is going to be very efficient, because as we get closer and closer to the query point, we're cutting out all the subtrees that are away. And again, in practice, the running time of this algorithm is going to be close to logarithmic. So in typical cases, the running time of nearest neighbor search in a 2D tree is going to be proportional to logarithmic. It is possible to concoct cases where you're going to have to examine all the points. For example, if they're all arranged in a circle and your query point's in the center, or something of that sort. But for typical data, it's very efficient. Now we're going to look at an application where we simulate a phenomenon in nature. And this is what kind of patterns do things like starlings and geese or cranes or fish or fireflies, how do they flock together? And we'll look at a simulation that corresponds to that.
And then, when the moment is right, they behave in a way that should be impossible. And it happens every day, right through the winter, just a couple of miles from my doorstep. How good is that?
So there's a simple model developed by Craig Reynolds a while ago for simulating this situation called the Boyd. And the idea is to use 3 simple rules to you get something very close to this complex flocking behavior. So you have collision avoidance, where you always try to point away from the k nearest Boyds. You have centering, where you try to point near the center of mass of the k nearest Boyds. And velocity matching, where you update your velocity to the average of the k nearest Boyds. And that algorithm works like this. So as that example shows, 2D trees are extremely effective in quickly processing huge amounts of geometric data. And what's more, it expands to more dimensions. With a very simple modification, we can take a 2D tree and create a data structure known as a KD tree, which even works for k dimensions. And the idea is, even if there's k dimension, what we'll do is recursively partition one dimension at a time. So that's called a KD tree. And we use the same idea as for 2D trees, but instead of cycling through just horizontal vertical, we cycle through however many dimensions there are. So it's in 3 space, we use a plane and do above and below, and then simply cycle through the dimensions. At level I, we put on the left the points whose ith coordinates are less than p, and on the right we put the points whose ith coordinates are greater than p's. And at cycle through the dimensions at level I mod k, we just use that dimension of the point to do the comparison. The implementation is simple, except for the comparison, and we get the same kind of partitioning for three-dimensional data. So we could do voids in 3 dimensions, or for databases with a large number of dimensions, you could do even much higher dimensional data and find nearest neighbors and do range searching extremely efficiently. It's a very efficient and simple data structure for processing k-dimensional data that's very widely used, and the whole idea is that data clusters, particularly in high dimensions. And also one point to make for this class is that this algorithm was discovered by an undergraduate in an algorithms class. So that's John Bentley, who discovered this while an undergraduate at Stanford. So it's a simple idea but expert scientists were struggling with dealing with huge amounts of geometric data, and Bentley found this way to process it efficiently that's been widely used ever since. And in particular, just as another example, consider the idea of n-body simulation, which is a classic problem in physics. Where you've got n particles mutually affected by gravity, and basically the computation is based on computing the interacting force for each pair of particles. And so then there'd be mutual gravitational pull, and this is what happens with a large number of particles in a certain simulation, and people understand properties in the universe by coming up with doing these kinds of calculations and comparing against what's observed in space. Now, but the thing is, for each pair of particles, so if you have n particles and you have to do it for each pair, that's n squared. So the progress of scientific investigation is going to be affected by how quickly you can do this calculation for a large number of particles. There's a lot of particles out in the universe, and you can't do a quadratic calculation for large n. Another undergraduate in an algorithms class discovered this idea for n-body simulation, and that's Andrew Appel. And his idea was that if some particle is way away from some cluster of particles, we can treat that cluster as a single aggregate particle and not do the individual force calculation between our particle and every one of those in the aggregate, but use the center of mass, and you get a very accurate approximation to the n-body doing that. And the algorithm that he used is based on 3D trees with the n particles as nodes and storing the center of the mass of the subtree in each node. And then to compute the total force traversing the tree, you have all the information that you need to complete the n-body calculation, but in time much closer to n log n than to n squared. And that idea that you didn't need to take time proportional to n squared, but with a geometric algorithm like a 3D tree, you could get the time to n log n, that enabled all sorts of new scientific investigation. And it's an example of the use of algorithms to enable new research.